All right, so we're going to jump into nuclear chemistry now. So nuclear chemistry. So this is what is used currently for diagnostic methods, right? So diagnostic methods. So you can think of these. I don't know if you've ever had them done or heard or know anybody that's done, but we use them for what call PET scans, CAT scans. They're used for cancer treatments. Right. So what happens is that we give patients are given radioactive materials to ingest, um, and what happens is when they ingest those, they put them under some equipment that will focus on those radioactive materials, right? Um, and able to see what's going on. And sometimes it takes hours. Sometimes it takes hours for that material to leave the body. Sometimes it'll take months for that material to leave the body. So just depending on the type of radioactive material that's given to the patient. But nuclear chemistry, nuclear chemistry involves reactions. So reactions that involve changes to nuclear structure. So reactions that involve change in nuclear structure, right? And we think of nuclear structure, right? We can simply just think of the nucleus, right? And in our nucleus, right, we have protons and we have neutrons. Right? So any change that's involving some change in the structure of a proton, some change in the structure of a neutron would be considered nuclear chemistry. So some things when we're talking, so in this particular chapter, when we talk about um, the number of protons, the number of protons in a nucleus, uh, we know this is equal to, just a reminder here, atomic mass. And we're going to use this capital Z here to represent the atomic number, to represent the number of protons in the nucleus. Nope, wait a minute. What am I doing here? Number of protons is just Z. Oh, sorry about that. The atomic, not atomic mass, atomic number. Atomic number, right? So the number of protons in the nucleus is atomic number, and we're just going to use Z to represent that value. Now, there we go. So we'll say the sum, right? The sum of protons um, and the sum of neutrons is equal to atomic mass. And we're going to use this value, this here, capital A. So capital A represents the atomic mass, and Z represents the number of protons or the atomic number. And an element, any isotope, right? Any element is going to be represented by this X here. So when we start looking at these nuclear reactions, right, we have a generic way of representing um, one of these nuclides or one of these isotopes here. And then we would put the atomic mass, uh, the atomic number, and then what element we have for it, right? So we can simply write something like carbon 14, which is radioactive, has 6 here. So this should look pretty familiar to you. I don't think you've gone this far without seeing something like this, right? This is how it is in the, when we look at something from the periodic table, it could look something very similar to this. But this is a radioactive form of carbon. Radioactive form of carbon. All right. So now that we got some of those parts, and we'll talk a little bit more, I'll mention a few other parts in the nucleus. Um, but as long as we're talking about the nucleus, so the force of attraction that holds the nucleus together is what we call the strong nuclear force. And let me write these down here. So the force of attraction that holds nucleus together is called strong nuclear force. Strong nuclear force. Now, strong nuclear force, this is one of the 4 fundamental forces, and I don't know if you've ever even heard of that term. The book doesn't discuss it, but I'm going to talk about it just a little bit. I think it's important to know here. But there is the strong nuclear force is simply just one of 4 fundamental forces. So the 4 forces are no particular order. That's not like one is better than the other, right? Um, One is gravity. Another one is electromagnetism. Another one is weak nuclear force. And then the fourth one is what we consider the strong nuclear force. So what holds the nucleus together is what we call the strong nuclear force. The weak nuclear force. The weak nuclear force is the force that can turn a neutron into a proton, right? The weak nuclear force is the force that can um, change a neutron into a proton, right? So when we talk about neutrons, and I'm not going to get too far into detail on this, but I just want you guys to have just some general idea when we're talking about, changing neutrons to protons and how that system works. Um, so let's consider this a neutron here, and neutrons generally have we're going to call it we're going to call them I'm going to call them down quarks. So this has 4 down quarks, and we have 1 up quark. Right? You might have heard that term quark before. And protons protons have what we're going to call, they have 3 down quarks and 1 up quark. So an up quark, uh, let me try. I'm going to try and this is going to represent an up quark here. So up quarks are generally positively charged here. So I'm just going to put a positive charge here, and generally these have a negative charge, the down quark. So think of down quark negative charge, and and don't think of it as being unbalanced or balanced. We're not unbalancing these, but there are enough down quarks here with enough negative charge to balance off this one up quark, right? So it's not like one electron, one proton, right? Is that there's enough negative charge with these four down quarks that they're going to offset the one positive charge of the up quark. So if our up quark is here, and let's put a down quark here. Let's put another one over here. Put another one over here, and we'll put another one over here. And these down quarks, right, surround this up quark here, right, and they kind of form this pyramid, that goes around this thing. So the weak force can turn this neutron, right, turn a neutron into a proton, right? So our neutron, here, this is our neutron, for one up quark, four down quarks. And what happens here is we get something called a neutrino. A neutrino is it's kind of like an electron, but has no charge, right? So this neutrino comes in with enough force, enough weak force here, to hit one of these down quarks and send it off here. And what that does is remember, right? I just mentioned here that the four down quarks are enough negative charge to offset that positive charge of the up quark, right? Well, if one of those gets knocked off by neutrino, right? This is how we get this neutron turning into a proton, right? Because now there's not enough negative charge, and now I have some positive charge from these down quarks. So energy that's associated with strong nuclear force is what we call nuclear binding energy. Nuclear binding energy. And nuclear binding energy can be calculated with, I'm going to spell his name wrong, with Einstein's what we call mass energy equivalence equation, right? If you've watched Big Bang enough, E equals mc squared, right? The mass energy equivalence equation, right? Where E is equal to energy, our binding energy, right? Uh, M is equal to mass, C is equal to the speed of light. And for the speed of light, we're going to use 3.00 times 10 to the 8th meters per second, right? And that's what we use to represent our speed of light here. So when we talk about this formula here, the units of Einstein's formula, are kilograms, meters squared, per second, per second, per mole. Right? So binding energy is going to be in terms of here kilograms per meter squared. I'm sorry, milligrams meter squared per second per mole. All right. But nuclear, as far as nuclear binding energy, right? We need nuclear binding energy converted in what we call electron volts. Electron volts, EV. And we do have a definition for that. So 1 electron volt is equal to 1.602 times 10 to the negative 19 joules. And it just so happens that 1 joule is equal to a kilogram meter squared per second per second. Right? So it's going to be really easy to convert the units of E equals mc squared into simply just joules. It'll end up just being joules per mole. So let's try and calculate this out. This is going to probably be a long workup because there is some other information needed in order to answer a type of question when we talk about binding energy. Right? So I'll pose the question here, and we'll say, what is the binding energy of one nuclei of this here? And let's see, I'm going to give you an AMU. So we'll say AMU of fluorine is equal to, I'm just going to round it to 19. 19 points, like 18.9998 or something. I'll just round it to 19. We'll be fine. So in order to calculate binding energy, there is a very first step here, right? Is that we actually have to calculate something that we call mass defect. Mass defect, right? Mass defect, this is our loss of mass. Our loss of mass, right? Because we're going to be converting, if we look at this formula here, right, we're converting mass into energy, which means we're going to have some loss of mass, and we have to be able to calculate that loss of mass, as we're converting mass into energy, right? Energy used to hold this particular nucleus together. So in order to calculate that, I'm going to give you some values here that you're going to need. Okay, so we're going to calculate we're going to calculate protons here. So a proton, I'm just going to P plus, is equal to 1.0073. And we're going to say that neutrons are equal to 1.0087 and electrons 0.000, nope, we'll just think just 3.00055, and we'll put AMU here. All right. So now we're going to add all of this up, right? If we're talking about this, well, let's go ahead and calculate that out using these values here, right? So what we have is I have, remember this, right? We're going to go back over here just as a reminder, right? A is equal to atomic mass, Z is equal to the number of protons, right? So we can definitely figure out the number of neutrons here. So the number of protons is 1.0073 times, let me scoot this over a little bit, 1.0073 times 9. And then we're going to go 1.0087 times, well, how many neutrons do we have? Somebody tell me. Just want to make sure you guys know.
10.
Yes, 0.0055. So we have 10 neutrons, and we have 19, nope, we have 9 electrons. All right. So calculator, 1.0073 times 9, 9.0657. 10.087 0045, and if I add all those up together, this, this is equal to 19.1572. 19.1572, right? And here is my atomic mass. So in order to figure this out, in order to calculate the mass defect, we're going to take 19.1572 minus 19.00 equals 0.1572. This is our mass defect, right? This is the mass that I'm going to use here. All right. So let's go ahead and calculate that value out now. And again, let's, you know what, this is in atomic mass units. All right. So atomic mass units, we can easily convert that into 0.01572 grams per mole. I'm going to put it this way here instead. Grams. You guys are pretty advanced here. All right, so this is what I just converted it into grams per mole, right? But we have to pay attention here, right? That this is in kilograms per mole. So we do have to make a quick conversion here. 1,000 grams, 1 kilogram. Be 0.001572 kilograms per mole. All right, so now that I have it in kilograms, now we can calculate this out, right? So we got energy is equal to 0.001572 kilograms per mole multiplied by c, our speed of light, 3.00 times 10 to the 8th meters per second squared. All right, can somebody calculate that out for me? And our units are going to be kilograms per mole, meters squared per second per second.
I got 1.4148 times 10 to the 14.
4148. So we'll just put 1 point times 10 to the
14.
14. All right. And again, let's go ahead because look at, don't forget here, 1 joule is equal to a kilogram meter squared per second is that we can calculate, we can easily convert this to 1.415 times 10 to the 14 joules because this, right? All that, let me erase that there, right? The kilogram meter squared per second. So we're just going to say that this is going to be joules per mole. But we're not quite done yet, right? We're not quite done yet because binding energy for one is in electron volts. And the question is asking us for one nuclei. Not for a nuclei that's in a mole of fluorine, but just simply one nuclei. Any ideas on how we can get rid of moles here? What can we use?
Could we possibly use what is it? Molar mass or no?
Not molar mass, because if we use molar mass, then we're going to be in joules per gram. I just simply want to get moles, right? Because I need to get nuclei. What if I ask this? If I were to ask you how many atoms are in 1 gram of something, what would you use?
Mm,
How many oh no, I shouldn't say gram. How many atoms in a mole of something? How many molecules in a mole of something?
Avogadro's, maybe?
Avogadros, yes. So we can use Avogadros. Let's see. So this is going to be joules per mole, and in 1 mole of anything, right, is 6.02 times 10 to the 23 nuclei,
oh yeah, I remember now.
right? And that will get rid of our moles here. All right, so let's do this calculation here. 1.415 times 10 to the 14 divided by 6.022 times 10 to the 23. And what did we get? Anybody verify it for me? Let's see. I got
I got
2 point.
2.35
Oh, yep,
times
sounds
10 to the
good.
negative 10.
10 to the negative 10. There we go. All right. And this is going to be in joules. That's going to be in joules. Okay, so we got 2.35 times 10 to the minus 10, 10 to the minus 10 joules. And I'm going to give you one more conversion. I'm going to put it up here, though, because I want these all in the same, or no, we already gave it to you. There it is. We're going to convert joules into electron volts. So 1.602 times 10 to the minus 19 to the minus 19, 1.602 times 10 to the minus 19. 1.602 times 10 to the minus 19 joules for 1 electron volt. And this value here, let's see, 2.35 times 10 to the minus 10. I get 1.47 times 10 to the 9 electron volts. And when we talk about nuclear chemistry, we usually don't talk about electron volts. We talk about, because there's so many electron volts, we convert this into what we call mega electron volts, right? Mega electron volts. And there's a million electron volts in just one mega electron volt. So we can do a quick conversion here, and we'd end up with 1.47 times 10 to the 3 mega electron volts, or just simply 147 mega electron volts. So this would be our answer here. So quite a few steps in here. I did have to introduce a lot of formulas in order to calculate that, but this is how we would calculate that binding uh, energy. And as far as the stability, right, the stability of the nucleus. So the stability of the nucleus is correlated to what we just calculated, binding energy per what we're going to call nucleon, per nucleon, right? And so we've calculated binding energy, and if you're wondering what a nucleon is, a nucleon is simply a proton or a neutron, right? And that's a nucleon, right? Proton, and neutrons are both nucleons. So if we want to figure out the stability of this fluorine, we can do that by simply taking a ratio of it. So we just calculated 147 mega electron volts. If we divide it by the number of nucleons, and all we need to do is look at the atomic mass for it here, 19. So in this particular nuclide, in this particular isotope here, we have 19. We're going to divide it by 19, and this comes out to 7.74 megaelectron volts per nucleon. And I'm going to show you, I need to show you the I'm going to write that before I switch to this page here. The higher this ratio is per nucleon, the more stable, right? The higher that value is, the more stable they are. And we tend to see this in higher mass elements. So if we look at this here, right, we have binding energy per nucleon, right, over the mass number, and we see where it starts to stabilize. If we take a look right halfway between the 40 and 60, the 60 mark, and I'll end up erasing it here, but right here, right around here is where we start to get this peak, right? Is that the binding energy is really weak. I mean, if we take a look at this, this binding energy is really weak up until we get to right between 40 and 60. So these here end up being a lot more stable than these here, right? Is that we're getting a stronger binding energy, and it does end up capping out. So the higher we get that, um, the higher the ratio is there, that value is, the more stable, right? The higher that ratio is, the more stable that value is. Now let me go. This is in my PDF, so I don't want to. I got to erase this before I. All right. Now let's look at other, we're going to look at particles that are in some of these nuclear reactions now. So let me start in a fresh page here. So particles in nuclear reactions. All right, so obviously we have protons. And when we represent proton in a reaction, because we are going to write reactions out, is that we're going to use this to represent a proton, right? Proton has a mass of 1 and 1 proton, obviously. So this is one way we can write it, or we can write it this way. And generally, this is how I end up writing it. So this is the one that you'll see me use the most, is it just if I'm going to eject a proton here, or not eject a proton, but convert a proton. And neutron will represent like this, where the mass is 1, but there are obviously no protons in that neutron, so we can represent it this way. Then we have what's called alpha particles, and I'll write it out here too. We'll put alpha. All right, we have what's called alpha particles. And an alpha particle is what we're going to consider. We consider these a high energy nuclei, right? An alpha particle, and I'll write that off to the side here as well. Is that's going to be a high energy nuclei, right? So our alpha particle we're going to represent like this: A for the atomic mass, Z for the number of protons, and then an alpha symbol, right? And just an example of this. So this is just an example. We would write it, a high energy nuclei would be something like a hydrogen that has 2 protons and a mass of 4, right? So we could simply write our alpha particle like this. Then we have beta particles, and I'll put beta down here. So we have beta particles, and beta particles are high energy electrons, high energy electrons. So we can write a beta particle like this, and then we'll put -1 here, and then we can write out the beta symbol, or I commonly use it like this, 0, -1, and we can just simply put an E there for an electron. But either or, it doesn't really matter which one you use. Generally, I use the E here for this one. And then we have one more symbol here. Is that we can have what we call positrons, right? So a positively charged electron. A positively charged electron. This is also known as the anti-electron. We can also call it instead of an electron, a positron. And this also has a symbol here, is that we use, instead of an electron, so it's something similar, but instead of -1, we put +1 and the beta symbol. Or we can say this, +1. So that's going to be our difference between our electron or beta particles and then what we're going to consider positrons here. Positrons are if you've ever heard of the word antimatter, right? Antimatter is that positrons are a great example of what we consider antimatter. So positrons, let me put this here. So positrons are antimatter. It's not the only antimatter, but positrons are an example of antimatter. Is that, when we consider what antimatter is, right? Um, those are just particles of the same mass, but an opposite state of another property, right? So, and I'll write that down. So particles of some mass, but opposite opposite state. How do I say that? But opposite state of another property, right? We have black holes, we have light holes, right? We have electrons, positrons, right? So something happens when antimatter meets matter, right? The whole world blows up. No, I'm just kidding, right? So something happens when matter and antimatter meet, is that this produces the Hulk. This produces something that we call gamma rays. Gamma rays have a symbol that we use here. It's like yeah, kind of like that. It's like an alpha symbol, but goes up, vertical. But this is what happens. This is how we get gamma rays. So we get antimatter to meet matter, right? And that produces what we consider to be gamma rays, right? So, for example, like we could simply just write it up, right? Is that we can go 0, -1, electron, right? So here's my high energy, just my beta particle here, plus a positron, and we're going to get, you know, we're going to get, you know, some gamma rays out of that, right? For the exam, though, I'm not going to be dealing with gamma rays on the exam. Gamma rays are, this is just kind of an intro to gamma rays, but this is as far as we're going with gamma rays, and I'm not going to put this on the exam. There's a lot more detail that goes into gamma rays here. So let's learn. We're going to balance. I'm going to put how, not learn, but we'll put how to balance nuclear equations. So there's a couple of rules and then a bunch of stuff to memorize, right? As far as balancing nuclear equations. So one of the rules that and these two rules we always abide by when we're balancing nuclear equations. When we balance nuclear equations, we take, so we'll write the sum of the mass numbers. The sum of the mass numbers of the reactants has to equal the sum of the mass numbers of the products, right? Law of conservation of mass. Whatever mass we start with, we have to have the same mass that we end with. And rule number 2 is the sum of charges. And I'll put of again. Of the reactants has to equal the sum of charge of the products, right? Law of conservation of energy, right? Whatever energy I start with is the same energy I have to have when we finish it, right? So there's different there's different types of nuclear reactions, and each nuclear reaction is laid out a different way. So I'm going to give you plenty of general formulas, and then we'll kind of decide which one to use. So one is that we're going to call what we consider alpha bombardment. And then we have what we can consider neutron bombardment. So for alpha bombardment, and remember, right, our alpha particle, right, and how we use that. So neutron, this is going to represent neutron, in our alpha. We can just simply use a z x here to represent that particular reactant or product here. All right, so let's do one with alpha bombardment, right? So I'm going to give you a problem here, and we'll say the production of O17 from nitrogen 14. By alpha bombard so the production of O17 from nitrogen 14. All right. So when we do alpha bombardment, the general formula that's used is we're going to take one element um, plus, let's see, we'll take it. sorry, my mic cut off. One nuclide and another nuclide, and then we're going to get a proton, plus we're going to get our new product here. So this is just kind of the general formula. We're going to fill out what A is, what Z is, what X is, and we'll fill those all out, but this is where we need to start for what we consider alpha bombardment, right? This is kind of the skeletal reaction that we're going to use. So the production of, so this is my product, this is my reactant. Well, let's go ahead and just simply start there. If I know that that's my product, nitrogen, 14. Does anybody know the atomic number for nitrogen? Go ahead and look at your periodic table. Somebody tell me. Because you are going to have to be doing this for the exam, for the homework, is consistently looking at a periodic table to get these. 7. Thank you, Christina. All right. So here, I'll just put 7. All right. So 7 plus this here, and I'm going to get 1, 1 here, plus I'm going to get oxygen. We know that to be 17. And what's the atomic number for oxygen? 8. All right. So going with rule number 1 and rule number 2, right? The sum of the masses of the reactants have to equal the sum of the product. Well, 18. The mass of the product is 18. Well, which means that this A down here, so I'm going to write this one more time, and we'll put 14, 7 nitrogen, plus this has to equal 4. Because 17 plus 1 is equal to 18, 14 plus 4 is equal to 18, so my masses are the same, right? These values down here also have to match. 9, so I can simply write a 2 over here. And what is the element with an atomic number of 2? Helium. So this is how we produce oxygen 17 from nitrogen 14, as we hit it with this alpha particle, right? This alpha particle of hydrogen here. This is our right alpha bombardment. We're hitting it with that, and we're going to get this new nuclide here. So this is kind of the general rule for alpha bombardment, but we do start with this just kind of general formula for that. So anytime we use alpha bombardment, start here, right, and kind of work your way down. Next, let's do neutron bombardment. And again, there's just kind of another general formula that we're going to use for that. We'll put AZX plus 1 neutron. And we're going to get another proton plus some other element. But there's actually 2 scenarios here. This is one scenario when we're doing neutron bombardment. So we could use this in a case where we're going from, let's say, carbon 14 to nitrogen 14, right? But neutron bombardment, because we're not adding, if we're only adding neutrons, we don't necessarily have to increase the number of protons. Right? If we're just adding neutrons here, doing a neutron bombardment, we could get another result here. And we'll use, this is the second general formula that we're going to use for that, is that we can still add the neutron, but we can simply just get this. And this would be used for something like, maybe we're going from uranium-238 to uranium-239. Right? We're just getting a different nuclide, different isotope of the same element. So one or the other, but it'll be stated in the question. It'll make it pretty obvious. If I just say we're converting uranium from 238 to 239, or from fluorine 19 to fluorine 21 or something like that. Like, it's pretty obvious which one you're going to be using here. So I'll give you. Let's use both of these examples that actually I've just given you. So the first one, we'll say carbon 14, and let me start. I'm gonna draw it in a different color so it's easier to follow. All right, so we're gonna say carbon 14, carbon, oh, come on. All right, so we'll say carbon 14, and that has 6 protons. We're gonna add 1 neutron to it, and we're converting this to nitrogen 14. So from that, we're gonna get 1 proton, plus we're going to get nitrogen 14, because that's what I've told you here, is that we're going to get carbon or nitrogen 14 from carbon 14. All right. So nitrogen has an atomic number of, using nitrogen 14. Maybe I was using boron in my example. Let's do, oh, let's see. I think I was using boron 14 in my example. So let's go with, yeah, there we go. Boron 14. Boron 14, which is atomic number 5. And our masses match. 14 plus 1 is 15. 14 plus 1 is 15. 6 here. 1 plus 5 is 6. So we end up, so everything is fine. We're perfectly fine with our masses here. The next one here, let's do uranium now. So we'll take uranium 238 plus 1 neutron, and we're going to simply just get, let's see, uranium 239. How much is in uranium here? 92. 92, 92. Let me clean that up a little bit. So 2 different examples that we have here when using neutron bombardment. And then I think the last one, I didn't write it up here, but we are going to talk about it real quick, and that's going to be what we call electron capture. So electron capture, our general formula for electron capture. So this is when we talk about if we're combining it with some, so many electrons. But electron capture We'll use this here. So we'll say plus a high energy electron. And we're going to get, yeah, so here's our general formula. So if I were to give you, let's say iodine 125 plus, right? I'm not adding, I'm not adding any mass to it. So the mass is the same. 125 plus 0 is still 125. And 35 minus 1, I'm sorry, that should be 53. 53? 53. Iodine 1. Yeah, it's down pretty low. And then this will be 52, right? 53 minus 1, we get 52. And 52 is technetium, Te. So this is what we're going to consider electron capture. And again, we just have kind of a general formula that we use for electron capture. All right. So this is when we bombard particles, right? We could still use these same rules when we talk about radioactive decay, right? So we've talked about neutron bombardment, alpha bombardment, electron capture. Is that now we'll consider radioactive decay. All right. So we have different types of radioactive decay as well. So first off, we have what's called, we've had alpha bombardment. Now we're going to have alpha decay. Right? So alpha decay, and we have a general formula for alpha decay. We're going to use ACX going to AZ alpha plus, right, for some alpha particle coming off. Then we're going to have what we call beta decay. There's two types of beta decays, right? Because we have two different types of beta particles. We have electrons, positrons. So positrons are, I don't know if I mentioned that earlier, positrons are also beta particles there. All right, so we're going to have beta decay. And I'm going to put a negative symbol here. So this is for, and I'll even write another term, call this electron emission. I think we can probably use that term here, electron emission for that, but not electron capture, but we can put electron emission. Right, beta decay, electron emission, and we can use this general formula, and we're going to eject an electron here, -1. And remember, you can always use this too. You can always use this -1 and the beta, you know, like that. It doesn't really matter which one you use. I just don't use that one too often. And then we'll put here. Then we're going to have more beta decay. So beta decay again, but this time with a positron, right? So, you know, positron emission. And we'll use the same, you know, we'll put not a fraction sign there. ZX, but this time we're going to eject a positron. And then we have gamma. So gamma decay. And I don't think I'm not going to put anything like this on the exam, but for that we would have ACX, and we'll have gamma rays don't, you know, put no protons, no mass for gamma plus AC. Right, there we go. So these are 4 types of radio decay that we're going to talk about. Radioactive decay. Right. So radioactive decay. When we look at the ratio between protons and neutrons, when we look at the number of neutrons versus the number of protons, um, is that we call this, we end up with something that, and there's a picture in your guys' book. I'm just going to draw it out. I don't want to go to the book yet. But we end up with a trail that looks something like this, right? And this is represents something that's, we'll say this is non-radioactive. So these are non-radioactive elements here. They kind of follow that trend here when we talk about the number of protons, the number of neutrons versus the number of protons. That eventually, in we end up with more neutrons than protons, and it ends up skewing that ratio. Instead of just going straight down the middle, it'll end up skewing that ratio off to another end here. And then our isotopes are all of our radioactive material ends up out here. So all of this here, our radioactive material ends up on the outside. This is what we call our band of stability, right? Here, this represents our band of stability. Our band of stability. So anything to the left, anything to the left, anything to the right. I'm going to write that down. Anything to the left or right of the band will decay into another nuclei that's in or closer to the band, right? So if we have something out here, it's going to decay to something that's either closer to the band or in the band, right? So it's going to, anything to the left or the right of the band will decay into another nuclei in or closer to the band. In or closer to the band. And I want to mention here that there's something, you might hear the term of something called magic numbers. So magic numbers, these are very stable isotopes, right? And there's no decay with them, right? There's no decay with them. So 2, 8, 20, no, oh yeah, 2, 28, 28, 50, 82, and 126. So these are elements here with these atomic numbers. These elements will not decay into another nuclei, right? They're stable. For some reason, they won't do, because they call them the magic numbers. So I don't want to put all the elements out there, but these are the atomic numbers for them. So as far as alpha decay is concerned, alpha decay occurs primarily for masses that are greater than masses that are greater than 200 for atomic numbers that are greater than 83. And this is where we're going to see alpha decay. As far as beta decay, so we have beta emission. So beta decay, where we're doing electron emission, beta decay have large neutron to proton ratios. So large neutron to proton ratio. And positron, right? Positron emission. So this beta decay, when we're ejecting positrons, have small neutron positron ratios, right? How do I know if it's high? How do I know large? How do I know if it's small, right? I got you. I got you guys. So we're going to use just simply the number 1. Anything where this proton ratio, neutron to proton ratio, is greater than 1 is going to be electron emission, beta decay, right? If it happens to be less than 1, we're going to do the positron emission, beta decay, right? So that's how we're going to be able to tell. There are some exceptions, that this isn't written in stone, but for an exam, I would make sure that it falls in line with this ratio. There are some exceptions like lead, helium, atoms that are or elements. It's this kind of a funny one. Elements that are from 9 to 19, 9 to 19 that are odd number atomic numbers. You don't even have to write that down. Like I just wanted to throw it out there, right? So I'll just make sure that it's not one of these exceptions. So but there are some exceptions to this rule when we use less than 1 or greater than 1. So I'm not even gonna. I'm just gonna actually erase this. I don't even want you guys to write that down and worry about it. So let's do a couple. We're actually going to determine what type of beta decay to use. Right? So if we were to use, let's say phosphorus 2815. Well, alpha decay, well, it's definitely not greater than 200 and it's not greater than 83. So alpha decay is not going to happen for phosphorus 28. Well, let's look at this ratio then. So from here, we're going to go the number of neutrons to the number of protons. So the number of neutrons here is 13 divided by the number of protons, and this is equal to 13 divided by 15, 0.87. Well, 0.87, that's less than 1. We're going to be doing positron, right? This beta decay, or we're going to end up tossing out a positron. So let's actually write a formula. Now we can write a formula up for that, right? Our formula for that happens to be this, right? A, Z, X. And we're going to give out 1 positive, right? Plus A, Z, X. All right. So let's start with that one there. So we're going to put 28, 15, phosphorus. We're going to toss out 1 positron here. And the mass didn't change, so we're still going to have the same mass, 28. And then we're going to have, what is this going to be, 16? And what atomic number is 16? This turns into sulfur. And I get sulfur because sulfur has 16 protons, atomic number 16. All right. Let's see here. What else can we do? How about if I were to put uranium 235. The uranium 235, well, that mass is larger than 200. The atomic number is larger than 83, is we're going to see alpha decay here, right? So this is alpha decay. Right. And we could, write up, alpha decay. I did give you some formulas for that. Alpha decay here. Uh, and actually, I don't even want you to write a formula up for that. Alpha particles. I'd have to give you the final one. I'd have to give you a final number there for an alpha decay. And I think that's just too much for this right now. So just know, we're just going to say that that this is going to be alpha decay. There's a lot going on with how to get a formula for alpha decay. But we can do some more beta decay. How about lithium 9-3? Right. So it's definitely not alpha decay. So what can we do here? It's got 6 neutrons, 3 protons. This is equal to 2, and that is going to be electron emission. For electron emission, we're going to say 9-3 lithium. We're doing this. Lithium electron. I lost my train of thought there. And that will become there we go. Wait, nope. Oh, what am I doing? Same thing happened. Let's correct this. Let's correct it. The formula is the same. Oh, yeah, my math is wrong here. Looking at these values, I have to have the same number of protons, which means that this has to be 4. 4 minus 1 is 3. So this ends up being 9, and this ends up being beryllium. And I'm pretty sure I made that same mistake above, so let's fix that. Because this equals 17, not 15. Which means this has to be 14, which makes this silicon. So please make those changes. I'm going to highlight those here. And I'm going to highlight this. Please make those corrections. My math was off there. All right. So a case have like this, so we'll say we have too few neutrons. We have too few neutrons, right? And this one has too many neutrons, right? So if we're doing electron emission, it's because we have too many neutrons. If we're doing positron emission, it's because we have too few neutrons. And almost done. I think we're just gonna, I'm probably going to, I'll just keep going. I'll keep going for right now. We might go in a little bit into the lab time, but I think we're gonna be okay. I gotta get through this stuff because we're gonna finish this on Tuesday. All right. So all nuclides, right? All nuclides, all these isotopes, right, have a half-life. We've kind of talked about this just a little bit, have this half-life where we use this here, T sub 1/2. Right? So radioactive decay rate, or rate of decay, doesn't really matter, it's okay. Radioactive decay rate is equal to what we call lambda n, where n is equal to the number of nuclei, and lambda is the decay rate constant. The decay rate constant. And we're just going to end up using these formulas here. We'll use these formulas here, 0.693, and I'll tell you where that value comes from. Originally, it's natural log of 2 over t 1/2, but we're not even going to use that one there. We're simply going to use this one here. We're going to calculate it already, 0.693 over t 1/2. Or we can write it this way. There is another way to write it. Or we can put t 1/2 is equal to 0.693 over lambda. So we're just going to talk about first order equations right now. So first order equations relating to n. First order equations relating to n, the number of nuclei, is that we're going to use these symbols here. We're going to use NT, and NT is the nuclei per mole at time t, right? And then N naught is just our initial nuclei per mole. And there's some more formulas that we need to know here. So this chapter, a lot of formulas here. NT is equal to N naught, E to the negative KT, or it is T is equal to negative 1 over lambda times the natural log of n sub t over n naught. All right. So now there's a lot of formulas here, but the formulas aren't difficult to use here. We'll do a couple of examples here. We'll use about radon 222. So radon 222, I'll write it this way as well. Let's go. Radon 222, 80. This is an 886. And the half-life here, the half-life for radon is 3.823 days. So the question here is going to be, how long will it take radon 222 with a mass of 0.750 grams to decay, leaving 0.100 grams? All right. How long will that take? All right. So the first thing we have to do is we actually have to calculate the radioactive decay rate, right? The radioactive decay rate, we know the half-life, right? So we know that we know the T1 half. So our T1, so our lambda is equal to 0.693 over 3.823 days. 693 divided by 3.823, and I get 0.1813 per day. Not tough there. All right. So now let's go. If we want to know how long it's going to take, right? Well, then we use our formula here. T equals 1/2. So T is equal to the time is equal to not 1/2, 1 over lambda, 1 over lambda, 0.1813 times the natural log, the mass at the time versus the original mass. So the mass at the time we're looking at is 0.100 minus the original mass here, 0.750. And this is equal to divided by 0.1813 times the natural log of, I get 11.2 days. Oops. 11.2 days. Let's do one more here. One more, and I think we'll call it a day. So not too bad. Just went 5 minutes over. How about we use technetium 99. Technetium 99. And let me get you well, we just need technetium 99. I can't, where is it at? Now it's going to bother me. Technetium. No, this is not technetium. That's why it's, there it is, number 43. That's not technetium. All right. So they use this in order to look at heart tissue, lung tissue, liver tissue, and that's what this is used for. So if we give you this has a half-life of about 6 hours. Right. So let's calculate the rate constant. So calculate the rate constant. Again, we're just going to use this formula. Lambda equals 0.693 over 6 hours equals divided by 6. There you go. So we're just going to be using, so mainly we are just going to be using a few of these formulas down here in order to calculate some of this information that they want. And I think that gets us through 3 sections of, well, the information I pulled out of those 3 sections, I pulled out this information that I wanted to make sure that you guys had. So I didn't completely go over this last section 3, but I did kind of cherry pick from it the important things that we need to take away from this class.